Spring 1945, Factory Number 22, Moscow. Andrei Tupolev stands on the concrete floor of a cavernous hangar, staring at 3 American B-29 superfortresses. 8 months ago, he was in the Gulag, designing aircraft in a labor camp Sharashka. Now, Stalin has handed him a directive that reads like a death sentence. Reverse engineer these bombers, bolt for bolt, rivet for rivet. No deviations, no improvements. Deliver a production-ready Soviet copy in 24 months or return to the camps. The B-29 is the most complex bomber ever built. Pressurized cabin, remote gun turrets, 4 Wright R-3350 engines producing 2,200 horsepower each. Tupolev's team has no blueprints, no tooling specs, no metallurgical data. Just 3 captured aircraft and 2 years to clone them perfectly. The clock starts now. 3 B-29s had force-landed in Soviet territory during bombing runs against Japan in 1944 and early 1945. Their crews were interned, then quietly released. The aircraft were not. Stalin saw an opportunity. The Soviet Union had no strategic bomber capable of reaching Western Europe with a meaningful payload, and designing one from scratch would take a decade. Tupolev's assignment is to short-circuit that timeline. His teams at OKB-156 and Factory Number 22 begin the painstaking work of disassembly. Every part must be cataloged, measured, sketched. Engineers estimate 105,000 individual components per aircraft, from structural frames down to oxygen regulator valves and cockpit light switches. Stalin's order is explicit and non-negotiable. Copy every component exactly as found. No design improvements, no simplifications, no substitutions of equivalent Soviet parts. If the Americans used a specific alloy or fastener, the Soviet version must match it precisely. Tupolev understands the subtext. Any deviation, however logical, could be interpreted as sabotage. The NKVD has embedded inspectors in every workshop. They will cross-reference every finished part against the American template. Tupolev has already survived 4 years in the Gulag on fabricated charges. He knows what failure looks like. His engineers receive the same message. This is not an engineering problem. It is a survival problem. Tupolev's engineers begin with hand tools, calipers, micrometers, protractors, no coordinate measuring machines, no photogrammetry, no computer-aided design. They measure each part multiple times to account for instrument error, then sketch cross-sections and note material properties by eye and feel. The Wright R-3350 engine alone contains more than 25,000 individual parts. Crankshaft journals, piston rings, valve springs, magneto gears, all specified in thousandths of an inch. The engineers must convert every dimension to metric, then figure out how to machine those dimensions on Soviet lathes and mills calibrated in millimeters. The first measurement logs fill entire filing cabinets within weeks. Soviet metallurgists at Factory Number 22 encounter the first major incompatibility in early 1946. The B-29's structural skins are specified in imperial sheet metal gauges: 0.032 inches, 0.040 inches, 0.051 inches. Soviet rolling mills produce aluminum alloy sheets in metric thicknesses: 0.8 millimeters, 1.0 millimeters, 1.2 millimeters. Direct conversion of 0.032 inches yields 0.8128 millimeters, which does not match any standard Soviet gauge. Rounding down to 0.8 millimeters means the skin is thinner than the original by about 0.013 millimeters. Rounding up to 1.0 millimeters makes it thicker and heavier. Neither option preserves the B-29's structural margins. The metallurgists draft a memo requesting guidance. The reply is terse. Match the American specification as closely as possible and document the deviation. OKB-19, Shvetsov's engine team faces a parallel crisis. The right R3350 crankshaft main bearing journals are machined to a tolerance of plus or minus 0.0005 inches. That is roughly 0.013 millimeters. Soviet calipers and micrometers, calibrated in metric, introduce rounding errors at every step of measurement and transcription. A dimension recorded as 3.250 inches might actually be 3.2498 or 3.2503 inches, but the metric conversion and machining process will treat it as exactly 82.55 millimeters. Over dozens of parts, bearings, bushings, piston pins, the cumulative drift can reach 0.05 millimeters or more. In a rotating assembly spinning at 2200 RPM, that slack translates to vibration, heat, and accelerated wear. Shvetsov's deputy warns that engine seizure in flight is a real possibility. In June 1946, the NKVD circulates an internal directive to all defense factories involved in the B-29 program. Any engineer who proposes a design change, substitutes a material, or omits a component without written authorization from Tupolev's office will be investigated for sabotage. The penalties are explicit: 10 years in the Gulag for negligence, execution for intentional deviation. Inspectors will compare finished parts to the American templates using overlay tracings and direct measurement. Discrepancies larger than machining tolerance will trigger immediate arrest. The memo lands on the desk of every section chief at factory number 22. One metallurgist quietly burns his notes, suggesting the use of a slightly harder Soviet aluminum alloy that would compensate for the thickness reduction. Another files a request to copy the B-29 skin gauge exactly, even though it weakens the structure. One of the interned B-29s carries a fabric patch on the navigator seat, likely a field repair made by a maintenance crew in the Pacific. Tupolev's team discovers it during disassembly and photographs it. The question circulates through the design bureau: do we replicate the patch? Engineering logic says no. It is a non-structural repair with no functional purpose. Political logic says yes. Any omission could be flagged as deviation. The story, later told by Soviet engineers, is that Tupolev himself made the call. Copy the patch exactly, stitch for stitch, and document it in the production manual. Whether the story is literally true or apocryphal, it captures the program's central absurdity. Terror demands perfection, even of imperfections. Late 1946, factory number 22. A production foreman named Alexei Voronov is inspecting the forward fuselage frame of one of the disassembled B-29s when he notices a small hole drilled in a non-structural stringer just aft of the cockpit bulkhead. It is not called out in any visible rivet pattern. It does not align with any fastener or cable run. It appears to be an accidental drill-through from the Boeing assembly line in Wichita, Kansas. Voronov brings it to his section chief. The chief brings it to Tupolov's deputy, who brings it to Tupolov. The question is simple: do we replicate the mistake? Omitting it is logical, but unauthorized. Including it introduces a stress concentration that could propagate cracks under pressurization. Tupolov makes the decision in under a minute. Copy the hole. Tupolev's deputy drafts a one-page memo for the NKVD file. The accidental hole is documented as an American specification, reference frame number and position coordinates provided. The memo states that the hole will be replicated in all Tu-4 production fuselages to ensure exact conformity with the template. No engineering justification is offered because none is requested. The same protocol is applied to the fabric seat patch, to a slightly misaligned rivet row in the bomb bay, and to a redundant lightning hole in a wing rib. Every anomaly becomes a specification. Every mistake becomes doctrine. The engineers understand what they are doing. They are building a plane that carries the political DNA of Stalinist terror into every rivet joint and bulkhead. The metallurgists finalized their decision on sheet thicknesses in early 1947. Where the B-29 uses .032-inch skin, The Tu-4 will use 0.8 mm Soviet alloy, a reduction of roughly 0.013 millimeters. Where the B-29 uses 0.040 inch, the Tu-4 will use 1.0 millimeter, an increase of about 0.016 millimeters. The engineers calculate that the average deviation across all skin panels is approximately 0.25 millimeters, or about 3% of nominal thickness. Load testing of sample rivet joints shows an 8% reduction in buckling resistance for the thinner panels. They judge this acceptable because the B-29's original design margins are generous, and because they have no other choice. The decision is documented and filed. Production tooling is ordered. The first fuselage sections begin rolling out in March 1947.
The rivet hole is always a structural weak point. When you drill through sheet metal, you remove material that was carrying tensile load. The stress that was spread across that material must now flow around the hole, concentrating at the hole's edge. In the B-29, the original American sheet thickness was sized to keep peak stress at rivet holes below the aluminum alloy's fatigue limit under normal flight loads. The Tu-4's thinner skins reduce the cross-sectional area carrying load, so peak stress at each rivet hole increases by roughly 8%. Under static load, this is survivable. Under cyclic load, thousands of pressurization cycles, turbulence, hard turns, microcracks can initiate at the rivet holes and propagate along rivet rows. The copy drill hole in the fuselage frame adds a second stress riser with no load-carrying function, concentrating stress by an estimated 35% locally when the cabin pressurizes. The Ash-73TK engine, the Soviet copy of the Wright R-3350, faces a different failure mode. The crankshaft main bearings require a radial clearance of roughly 0.05 to 0.08 millimeters to allow an oil film that prevents metal-to-metal contact. The metric conversion and machining rounding introduced an average clearance error of about 0.05 millimeters, enough to widen the gap beyond design spec. At idle and low power, the thicker oil film is stable. At 2200 RPM and high manifold pressure, centrifugal force and combustion loads squeeze the oil film thinner. If clearance is too large, the film breaks down, allowing the crankshaft journal to contact the bearing shell. Friction generates heat. Temperature rises 15 to 20 degrees Celsius within minutes. The bearing material begins to soften. Without intervention, seizure follows within 50 flight hours.
The B-29 was the first production bomber with a fully pressurized cabin, maintaining an 8 psi differential between inside and outside at altitude. That pressure pushes outward on every square inch of fuselage skin, trying to inflate the fuselage like a balloon. The load is carried by the skins in hoop tension and transferred into the frames and stringers through rivet joints. Each rivet must resist both shear load, sliding between skin and frame, and bearing load, where the rivet presses against the edge of the hole. The copied drill hole in the fuselage frame interrupts the load path. Stress that should distribute evenly along the stringer must now bypass the hole, creating a local hotspot. Finite element analysis, unavailable to Soviet engineers in 1947, would later show that peak stress at the hole edge is 35% higher than in the surrounding structure. If a crack initiates there, it will grow with every pressurization cycle. Aluminum alloys do not have a true fatigue limit. Below a certain stress level, they can endure millions of cycles. Above that threshold, every cycle grows a crack incrementally. The B-29 was designed for a service life of about 400 flight hours and 500 pressurization cycles. Soviet engineers assumed the Tu-4 must meet the same target. The thinner skins in the copied drill hole raise peak stress at critical points by 8 to 35%, moving them closer to, or in some cases above, the threshold where crack initiation becomes probable. Every takeoff, every climb to altitude, every turbulence bump, and every pressurization cycle
is another tick of the fatigue clock. The engineers know this. They document the risk in internal memos. They also know that grounding the program is not an option. Stalin's deadline is May 1947. First flight is scheduled for that month.
May 19, 1947. Factory number 22 Airfield. Test pilot Nikolai Rybko advances the throttles on the first Tu-4 prototype. 4 ASH-73TK engines spool up with a deep roar. Tupolev, his deputies, and a cadre of NKVD observers watch from the control tower. Rybko releases the brakes. The bomber accelerates down the runway, tail lifts at 80 knots, and at 140 knots the main gear separates from concrete. Gear retracts cleanly. Rybko banks gently to the north and begins a climb to 8,000 feet. Engine instruments are stable, oil pressure normal, cylinder head temperatures within limits, manifold pressure holding. No abnormal vibration in the control yoke. For the first 10 minutes, the Tu-4 flies like a B-29. Tupolev exhales, but does not relax. At 12,000 feet, Rybko activates the cabin pressurization system. Compressor bleed air from the engines flows into the fuselage, and cabin altitude stabilizes at 4,000 feet, an 8 psi differential. The fuselage creaks audibly over the intercom as the skins stretch outward under hoop stress. Rybko reports the sound to the tower. Tupolev's deputy notes it in the flight log, but does not order abort. The creak is expected. The B-29 made the same sound. Then a sharp metallic pop echoes through the cabin. A rivet near the waist gunner station has sheared, leaving a small hole. Cabin pressure begins to bleed. Rybko throttles back the pressurization to 6 psi and holds altitude. The leak stabilizes. He keys the radio and reports the rivet failure. Tupolev tells him to continue the test. Rybko monitors the engine instruments. ASH-73TK number 3, starboard inboard, is running hot. Cylinder head temperature climbs from 220 to 245 degrees Celsius, approaching the 260-degree red line. Oil temperature follows, rising to 95 degrees. The gauge needles creep upward slowly, but steadily. Rybko enriches the fuel mixture slightly, trading power for cooling. The temperature stabilizes at 245 degrees, but does not drop. He reports the condition to the tower. Tupolev consults with Shvetsov's engine lead over the telephone. The lead says the bearing clearance error is likely causing friction and heat, but if temperature holds below redline, the engine should survive the test flight. Tupolev relays the instruction. Continue, monitor closely, abort immediately if temperature exceeds 250. Rybko holds altitude and power for 10 minutes, exactly as briefed. Engine 3 remains at 245 degrees. The cabin pressure leak is stable at 6 psi. No additional rivet failures. At 25 minutes elapsed, he begins descent. Throttles back. Cabin pressure bleeds off. Engine temperatures drop. By 5,000 feet, all instruments are back in normal range. Rybko extends gear and flaps, lines up on the runway, and lands smoothly. Ground crew rushes to the aircraft as the engines shut down. Tupolev and his team descend from the tower and walk to the flight line. The first flight lasted 32 minutes. The Tu-4 did not break apart in the air. It did not catch fire. The program survives. Engineers swarm the Tu-4 with flashlights and magnifying glasses. The popped rivet near the waist gunner station left a clean hole. The surrounding rivets show no deformation. Farther forward, they find micro cracks radiating from 2 rivet joints in the fuselage skin, each about 5 millimeters long. The cracks originated at the rivet holes and propagated along the grain of the aluminum. Near the copied drill hole in the forward fuselage frame, they find visible deformation. The hole has elongated slightly under stress, and a hairline crack extends 3 millimeters from the hole edge. None of the cracks are immediately dangerous, but all of them will grow with continued pressurization cycling. The inspection team photographs each defect and catalogs them in the flight test report. Tupolev reads the report that evening. Tupolev's team drafts a series of design changes, the first deviations from the American template permitted since the program began. Rivet joints showing cracks will be reinforced with doublers, thin aluminum straps riveted over the joint to distribute load. The copied drill hole in the fuselage frame will be reamed out and fitted with a flush plug. Then the frame will be locally reinforced with a bonded patch. Shvetsov's engine team adjusts the ASH-73TK crankshaft bearing clearances, tightening them by 0.02 millimeters to bring them back within Wright R3350 specifications. The changes are documented, approved by Stalin's Defense Committee, and incorporated into production tooling. By late 1947, the Tu-4 passes state acceptance trials. The structural reinforcements eliminate the rivet failures. Engine temperatures remain stable through extended high-altitude flight testing. August 3, 1947. Stalin orders a flight of 3 Tu-4 bombers over Moscow's Tushino airfield during the annual Aviation Day parade. Western military attachés watch from the reviewing stand as the silver bombers thunder overhead in tight formation. The aircraft are visually indistinguishable from American B-29s. U.S. intelligence officers are stunned. They had assumed Soviet industry lacked the precision tooling and metallurgical expertise to replicate the superfortress. The parade is Stalin's public declaration that the Soviet Union now possesses strategic bombing capability. Production ramps up at 3 factories: Kazan, Kuibyshev, and Moscow. By 1949, over 800 Tu-4s are in operational service, deployed to bomber regiments in the Western Soviet Union and the Far East. The Tu-4, like the B-29, has a combat radius of roughly 3,200 kilometers with a full bomb load. From bases in the Western Soviet Union, that range barely reaches the coastlines of Western Europe. A one-way suicide mission could reach New York or Washington, but not with any expectation of return. The Tu-4 gives Stalin a credible threat against Europe and a propaganda victory over the United States. But it does not give him true intercontinental strike capability. Soviet planners begin studying aerial refueling and forward basing options. The Tu-4 will serve as the backbone of Soviet strategic aviation until the first jet bombers, Myasishchev's M4 and Tupolev's own Tu-16, enter service in the mid-1950s. The imperial to metric conversion crisis forces a bureaucratic overhaul across Soviet aviation. In 1948, the Ministry of Aviation Industry issues new design standards, mandating that all future aircraft programs use metric units exclusively. Tooling, material specifications, and tolerance chains must align with Soviet manufacturing capabilities from the start. Reverse engineering will no longer be the default path to advanced technology. Indigenous design, informed by captured knowledge but not enslaved to it, becomes the new doctrine. The Tu-4 program's lessons shape the development of the MiG-15 jet fighter, the Tu-16 bomber, and eventually the space program. Soviet engineers learned to measure twice, cut once, and never again replicate an accidental drill hole. Andrei Tupolev survives the Tu-4 program and receives the Stalin Prize in 1948. He avoids the Gulag. His design bureau, OKB-156, goes on to design the Tu-16, the Tu-95 turboprop strategic bomber, and the Tu-104 jet airliner. Tupolev becomes one of the most powerful figures in Soviet aviation, his wartime imprisonment a cautionary memory, but no longer a threat. Many of his engineers and deputies are also honored, their compliance rewarded with medals and apartments in Moscow. The terror that drove the Tu-4 program does not vanish, but it recedes slightly as Stalin ages. The program proves that even under extreme political constraint, competent engineers can deliver functional hardware, if they are willing to replicate every mistake their adversaries made. One of the original B-29s interned in 1945 survives in a Soviet museum, partially disassembled, its aluminum skin still bearing the faded U.S. Army Air Force's star and bar insignia. The Tu-4 itself remains in service until the early 1960s, gradually replaced by jet bombers.
Several airframes are preserved in Russian aviation museums. Visitors can walk beneath the wings and peer into the bomb bay, seeing the rivet rows and frame stringers that once carried the weight of Stalin's ultimatum. The fabric seat patch, if it was ever truly copied, is no longer visible. The accidental drill hole, if it still exists, is unmarked. The bombers are silent now, their engines cold, their terror bureaucratized into history. The Tu-4 never dropped a bomb in anger. It served as a strategic deterrent, a training platform, and briefly as a test bed for early Soviet atomic weapons. In 1951, a Tu-4 dropped the Soviet Union's second atomic bomb during a test at Semipalatinsk. The bomber's pressurized cabin and high-altitude capability made it suitable for nuclear delivery, though by the mid-1950s, faster jet bombers had taken over that role. Some Tu-4s were converted into reconnaissance platforms, tankers, and airborne early warning aircraft. The type accumulated thousands of flight hours across dozens of regiments, and while structural cracks occasionally appeared at rivet joints and frame intersections, none caused catastrophic in-flight failures. The metric errors and copy defects, reinforced after first flight, proved survivable. Western intelligence spent years trying to determine how the Soviets copied the B-29 so quickly. Some analysts suspected espionage, that Soviet agents had stolen blueprints or bribed Boeing engineers. Declassified files later confirmed that no such intelligence coup occurred. The Soviets had no blueprints. They had 3 airplanes, calipers, and 2 years. The reverse engineering was legitimate, if brutal. The most valuable intelligence the West extracted from the Tu-4 program was not technical, but psychological. It revealed the degree to which Stalin was willing to terrorize his own engineers to close the technology gap. That willingness, more than any bomber, shaped Western Cold War strategy for the next 4 decades. The Tu-4 stands as one of the most faithful copies of a complex machine ever executed under wartime pressure. It also stands as proof that perfect replication, when forced by terror, is harder than original design. Tupolov's engineers could have built a capable strategic bomber in 5 years with a clean sheet design, learning from the B-29's principles, without slavishly copying its rivets. Instead, they spent 2 years measuring, converting, and replicating every detail, including the stakes, because deviation meant death. The result was a functional bomber that matched its template almost exactly, and a generation of Soviet engineers who learned that political survival and technical excellence are not always aligned. That lesson, encoded in aluminum and rivet steel, is the Tu-4's most enduring legacy.